Hello everyone, I'm Yingjie Qi from Beihang University. On behalf of our research group, today I'll be presenting our work titled CIMFlow, an integrated framework for systematic design and evaluation of digital SIM architectures. Here is a brief outline of today's presentation. Let's start by introducing the background and motivation. As we all know, artificial intelligence has witnessed unprecedented growth in recent years. But as the capabilities of AI models continue to evolve, their compute and memory demands are also increasing at an exponential rate. As a result, we're transitioning from a compute-limited era into a memory and bandwidth-limited era. Although many DN accelerators have been proposed, due to their separate compute and memory resources, traditional von Neumann-based architectures still require frequent data movement between compute and memory. This issue is also known as the memory wall bottleneck. To mitigate this challenge, the compute in memory, or CIM paradigm, has been proposed. CIM architectures embed computation within memory arrays, which effectively reduces the cost of data movement while also offer great computation parallelism. CIM can be broadly categorized into analog and digital implementations. Unlike analog CIM, which performs multiply and accumulate operations using voltage or current in the analog domain, digital CIM embeds digital logic units directly into memory arrays, providing more robust computation and enhanced parallelism. This makes digital SIM a promising candidate for DN acceleration. However, realizing the full potential of digital SIM in DN acceleration is a collaborative effort, which requires co-optimization across multiple design levels, including DN workload, software design tool, and SIM architecture design. Moreover, as the landscape of DN workload and SIM architecture design grows more and more complex, determining the optimal software-hardware design choice also becomes increasingly challenging. In order to bridge the gap between DN models and hardware design, navigating through this expansive design space would require flexible software-level support. Therefore, developing dedicated tools that are aware of digital SIM characteristics is also essential for the real-world adoption of digital SIM. Although there has been several software tools or frameworks aiming to tackle these challenges, most of them only provide support for specific aspects of the design flow, such as compilation or simulation. The lack of integration between design stages greatly limits their capabilities in exploring the software-hardware design space as a whole. Moreover, existing tools often adopt fixed architectural or model assumptions or use tightly coupled co-designs, which limits their flexibility when faced with the evolving design space. Finally, due to their prominence in current research, existing tools tend to primarily focus on supporting analog SIM, often overlooking constraints such as the capacity limitations in the SRAM-based digital SIM. These limitations motivate us to design an integrated framework to provide support across the entire design flow. To this end, we propose the CIMFlow framework. The framework consists of an extensible instruction set architecture, a compiler, and a simulator. The ISA, serving as a bridge between the other two components, is composed of hierarchical hardware abstraction and a flexible instruction set design. In addition, the compiler performs optimizations tailored for the resource constraints of digital SIM. And the compiled instruction flow will be executed on a cycle-accurate simulator for detailed performance analysis. In short, CIMFlow aims to address the aforementioned limitations by providing an out-of-the-box workflow that offers integration, extensibility, and specialized optimization. Now we will go over each component within the framework. The ISA design in CIMFlow consists of a three-level hardware abstraction and a flexible instruction set design. To ensure scalability, CIMFlow adopts a multi-core architecture at the top level, with each core being a basic unit of program execution with its own instruction flow. A core can then be broken down into a series of units that perform specific operations. Each abstraction level interfaces with a corresponding component or stage in the compiler and simulator. The instruction design in CIMFlow adopts a unified 32-bit format, with reserved encoding for future extensibility. To be specific, the chip-level abstraction consists of multiple cores and a global memory interconnected through a network-on-chip structure, which supports flexible intercore pipelining among operators. And the core-level abstraction includes a series of resources, such as compute units, memories, and control logic. All memories, including the CIM units, share a unified address space, which greatly streamlines the data management implementation in compiler and simulator. At the unit level, the abstraction includes the description of multiple compute units, such as CIM compute unit for executing the MEM operations, vector compute unit for accelerate DNA operations, and scalar compute unit for facilitating the control flow. In particular, the CIM compute unit contains a series of macro groups, which are groups of macros that stores the same weight where each macro shares the same input. The organization structure ensures flexibility of parallelism in both input and weight dimension. Moreover, the instructions in CIMFlow can be categorized into compute, communication, and control instructions. The unified format streamlines the instruction decoding process while also leaves rooms for future extension. Based on the EISA design, the CIMFlow compiler is responsible for translating the DM models into instructions that the CIM architecture can understand. This process involves optimization at both computation graph level and the operator level. The former maps the workload across multiple cores, while the latter further optimizes the partition workload within each core. Due to the capacity limitations of digital CIM, not all models can fit entirely on chip. The CG level optimization tackles this challenge by applying a dynamic programming-based model partitioning technique. By partitioning the model into several execution stages and applying the core level weight duplication according to the estimated cost, the CG level optimization can efficiently map the DM workload across cores and generate the operator sequence for each core. The OP level optimization takes the generated sequence for a single core as input and first performs virtual mapping, where the weight dimension in a nested loop format are mapped onto a virtual two-dimensional array without constraints. It then performs the physical mapping, where optimizations such as loop transformations are applied regarding to the hardware descriptions. Finally, the compiler generates the instruction flow according to the ISA definition, and the code are sent to the simulator for execution. The simulator in CIMFlow is a cycle-accurate system C-based simulator. It performs behavior simulation according to the hardware abstractions defined in the ISA, and generates a comprehensive performance report for a given workload. The simulator supports a fine-grained pipeline modeling, which includes the core-level control pipeline with a bitmap-based scoreboard for conflict handling, as well as a customizable unit-level computation pipeline for the compute units. The simulator also supports flexible architecture parameter configuration and allows integration of custom architecture components by adopting a modular interface. After behavior simulation, the performance evaluation will analyze the simulated execution results and produce an overall performance report with detailed breakdown across multiple design levels. Next part is the evaluation. We evaluated CIMFlow with 4 DM models, including 2 computation-intensive models, ResNet and VGG, and 2 compact models, MobileNet and EfficientNet. The default architecture is a 64-core architecture, with the CIM compute unit having 16 macro groups per core and 8 macros per group. The performance parameters are all extracted from industry standard or open source tools. We compare our dynamic programming-based technique with generic mapping and opportunistic operator duplication method. The results have shown that our method achieves up to 2.8 times speedup and 61.7% energy reduction. The optimization is particularly effective on compact models, since conventional methods tend to leave fewer cores unoccupied within each execution stage, thus limiting the opportunities for duplication. We also explore the trade-offs in architecture configuration through 2 key design parameters: macro group size, which corresponds to the amount of compute resources, and NOC bandwidth, which is closely related to the communication cost. The results have shown that for compute-intensive models, increasing the amount of compute resources or bandwidth will generally improve throughput. However, for compact models, this might not be the case. Increasing the macro count only brings limited throughput gains, and higher bandwidth would introduce higher transfer overhead. We further illustrate the software-hardware design space across these configurations and different compilation methods. The results have shown that although the hardware configuration sets the upper bound of achievable performance, software optimizations are also crucial in realizing the hardware's potential. Therefore, separate optimizations may lead to suboptimal solutions, which also validates the integrated design approach adopted by CIMFlow. Finally, here's the conclusion of our work. In this work, we present CIMFlow, an integrated framework that addresses key challenges in digital SIM design through a multi-level ISA design, advanced compilation strategies, and an extensible simulator. We hope that the customizable and extensible nature of the framework will be helpful for researchers and designers in the future. The code and documentation will soon be available at CIMFlow.org. That will be all for my presentation. Thank you for listening.